Okay. Ugh. Everybody signed up for the hackathon?
Yep.
Okay. Did everybody go to the CS get together? I didn't see Charlie there, did I? You were there? Are you lying? Okay. Did you win anything? Oh, like a USB stick? Anybody get anything better than that? Anybody have good prizes? Oh, a Samsung tablet? Is it Samsung or just an Android one? It's a good one, right? Probably nobody beats the tablet. Maybe get like the chocolate bunny. When the Pop Tarts started having a cult following, it seemed like. That's where it's at. All right. Number one, why are arrays considered? Oh, I guess quick. The grades were fine. Low grade, I think, was like a 40 something. High grade was 100, I believe, or like a high 90, something like that. So overall, grades were fine. I think class average was, 75 or 78, something like that. All right, why are arrays considered to be fast and linked lists considered to be slow? Well, I handed his test back. Oh, go ahead. Tell me.
Arrays have constant time access.
All right, well, so that's a little technical. Why do they have constant time access?
It just takes one command to access any given element of an array.
Why?
Because they're specific contiguous memory.
That's the thing. That's the kicker.
To get it, whereas with linked lists, you have to go, okay, what's this guy pointing to? What's this guy pointing to?
Yeah. So the contiguous memory is a very important thing, right? So arrays are fast because they are implemented using contiguous memory in a row. Okay, what else am I supposed to say? Okay. Linked lists are considered slow. And you might say slow but memory efficient. So arrays are considered to be memory inefficient. Linked lists are memory efficient. Linked lists are slow because one must traverse the list from the beginning or potentially end and walk through memory, i.e. not implemented in contiguous memory. Okay, so that's a contiguous memory thing. All right, questions about that? All right, number two, stack stuff. What are the functions of a stack? Push, pop, peek. All right, I did mention in class that officially peek isn't necessarily considered an official requirement for it, but you will always find peek to be handy. So push adds a new element to the top of the stack. Pop removes an existing element from the top of the stack. Peek shows the element at the top of the stack without removing it. Those are our three stack functions. All right, questions about that one? All right, number three, convert value from binary to hex. Let's see, this is, what's the value? 1, 1, 0, 1, 1, 1, 0, 0. All right, so we need to convert this guy from binary to hex. We use our trick into groups of 4, right? So we have 1101 and we have 1100, 1100. This is the ones place, the twos place, the fours place, the eights place. So this is a 12. This is the ones place, the twos place, the fours place, the eights place. So this is a 13. So that is what D. See? That's the conversion, DC. If you didn't remember that you needed the trick and you wanted to do it the long way, you could have. So let's do that. So ones place, twos place, fours, eights, 16s, 32s, 64, 128. Ones, twos, fours, 8s, 16s, 32, 64, 128. Yep. Oh. So that's 220 in decimal. Then we're going to convert 220 to hex. So 220 divided by 16 is 13. 13 times 16 is 208. So that's a remainder of 12. 13 divided by 16 is 0. 0 times 16 is 0, with a remainder of 13. This is a D. This is a C. We read it from bottom up. There's DC. Make sense? All right. I think too many people missed that one. Write an error-free Hello World program, our old friend. So public, huh?
What language do you want?
I think the presume was Java, but if you wrote it in something else, that's fine. So public class hello. That should be a lowercase p. I'll fix them in the end. Public static void main string array args system.out.println hello world, and of course you had to have, how many do I have? Exactly 6 exclamation points, otherwise it was all wrong. So for it to be a program, you need to have it inside of a class, not just the method. So public class hello, call the class whatever you want. Opening, closing curly braces inside of there. Public static void main, string array. You could have named it args, which is the traditional, but you can name it whatever you want. And then system.out.println hello world. So there's your hello world in Java, error free. Questions about that one? Okay. All right, so for the next questions, you can assume there exists a stack and a linked list object that are capable of holding integers. You can make a reasonable assumption. You can only make one assumption, okay, across the board. So you pick your favorite assumption regarding the methods that each of these data structures already have. So number 5, write a recursive method. Emphasis, remind me, what does recursion mean? That's almost as good as your constant time answer. What's recursion? Yeah, so functions implemented in terms of itself, or a function calls itself, something like that. Right, so this had to be a recursive version of this guy that takes a stack and prints to the screen the contents of the stack. you do not have to preserve the contents of the stack, okay? And what did I say to call it? Oh, it didn't say to call anything. So we're just call this guy printstack. So we're going to say void printstack, and this guy will take a stack S as a parameter. All right. Now we're going to ask the question if not s dot is empty, something like that. So we can assume that is empty exists, or if you want to write that differently, you can say if s dot peak not equal to null. That's the same thing as asking whether it's empty, right? So if there's still stuff in the stack, then what are we going to do? We're going to do a system.out.println s.pop.getPayload. Keep in mind that if you just print out s.pop, you're going to get a crazy looking memory address, right? It's going to be the node. Now, you could have assumed that s.pop returned the payload of it, and I guess that's fine. But, you know, s.pop.getPayload if this guy returns the node. Pick your poison. All right, so after I do that, s.pop does permanently change the stack, correct? Stack is now short one element. So then what I'll do is I'm going to go ahead and call printstack passing s. I'll go ahead and call the exact same function, passing my new stack to it. That's one short of what it used to be, and let it do this exact same thing. So it's going to, as long as there's stuff in the stack, it'll pop it and print it and call this function again. As soon as we have something that's empty, it stops printing. And the part about you do not have to preserve the stack, we have in memory emptied the entire stack. So whoever used to have this stack no longer has stuff in their stack. So we did not preserve the structure of the stack. All right, questions on that one? Well, it would take more work, and doing it recursively would then be more difficult because you'd probably have to pass in a second stack along with it. That is your starts off as the empty stack and then starts building up. It's the replacements of your old guy. But yeah, it would be not incredibly difficult, but annoying. It would be annoying to preserve the. So I made it easy by not making you preserve the contents of the stack. All right, what number was that? 5. All right, number 6. Write a method named index of that takes a linked list and an integer for which to search. The method should return the index where that int is first found, or -1 if it's not present in the list. Okay, so we're effectively writing the strings index of method, but for linked lists. That dude. All right. I'll do it on this same screen. Ooh, I might be able to. Whatever. Index of linked list LL int n. We'll say that's the guy we're searching for. Okay, so who? Oh yeah, it's returning the position. Yeah, I copied this. I shouldn't have copied that. All right, so index of. So we're going to search through our list, looking for the value, returning the index of that value. You can assume that you have like an is empty if you wanted to. Otherwise, you can just check the head of the list or something like that. You can kind of decide. But I'm going to create an int. A little more indentation there. Pause. We'll start this guy off at 0. You could also assume that you have a count for your linked list. That would work as well. So maybe the most straightforward version of this might be for int I is equal to 0, I is less than ll dot get count I plus plus. I usually do 2 spaces. I did 3 this time. I know it's happened to me all. I'm all off. I'm discombobulated. What was I doing? Oh, yeah. So we're going to ask if the current guy we're looking at is the value we're looking for. So we'll say if ll dot get at bucket I dot get payload, if that guy is equal to n, sort of. Then we will return I if we found it. Otherwise, we'll keep trucking. If we survive the entire linked list, we'll return a -1. And then uncapitalize some of these things. So something along those lines. Yeah, so this is going to be the node that lives at bucket I in our linked list. We're going to get the payload of that node, which is going to be a value. And I want to know if that guy is equal to the integer we're searching for. If it's equal to the integer we're searching for, then I'll go ahead and I'll return the position I found that guy in. Otherwise, return -1. All right, so in this case, we made the assumption that there's a get count and then there's a get at a particular bucket. You wanted to go ahead and go through and kind of piece apart your linked list. I'll kind of show you that version. And this kind of presumes that your linked list is filled up with some public variables, maybe. So maybe we say node cur node is equal to ll dot, you can maybe say get at bucket 0 or ll dot head, get you the front of the list, while cur node is not equal to null. We're going to do some stuff. What stuff we're going to do? We're going to ask the question if cur node dot get payload is equal to n, then we want to return something. What do we want to return? We want to return the current position that we're at. So we have to keep track of position. So when pos starts off at 0, return pos. If it's not found there, we're going to definitely say pos ++ to move down the list. And then we're also going to say cur node is equal to cur node dot get next node. If we survive this while loop and never return anything, return a -1. Something along those lines. That's the walk it with the node stuff. And here we'll fix my capitalization a couple of places here. Something like that. Questions on that one? All right, next one. Method. Reverse list, right? Okay. The original in reverse. All right, we're going to be returning a linked list called reverse. Did I say reverse list? What did I call it? Just reverse? Reverse list. This guy's going to take a linked list as a parameter, And we're going to return a new linked list that is the original in reverse. So we're going to say linked list answer is equal to new linked list. So we got a nice empty linked list. Then we're going to go through and walk our original list. So we'll use a similar approach to our for loop from the previous one. So for int I is equal to 0, I is less than ll.getCount, I plus plus. And we'll say answer dot add end. Now, a couple things we do need to consider here. So do I say anything about preserving the original list? Now, I didn't take off of this, but this is actually an interesting thing. So I'm going to write it the kind of the straightforward way, and then I want to talk about the weaknesses of that. So answer add end. Actually, we're going to add front from ll.get from bucket 0, something like that. So we're getting the current, well, ll at bucket I rather. So we're getting the current element we're looking at. So bucket 0, then bucket 1, then bucket 2, then bucket 3 from ll, and we're adding it to the front of answer. So we'll add bucket 0 to the front of answer, then bucket 1 to the front of answer, then bucket 2 to the front of answer. So we're building answer backwards by always adding to the front of it. Make sense? So when this is all said and done, and the presumption here is that get is not removing an element from the linked list. All right, and I want to talk about this in a second. So in the end, answer should be the original list in reverse. So we're going to go ahead and return answer. All right, so we look at something like that, we'd say that looks correct. All right, and I would have given you points for that. What's potentially wrong with this? Assuming that get does what I said. It returns the node that lives at a certain spot, but doesn't actually disconnect it. This is a nice fun one. Say this again. Well, I think you're along the right lines here. You're probably breaking your original linked list, because when I get, so let's say I get bucket 0 from the original linked list, but I haven't disconnected it. That's still the head of my first linked list. Okay, but then I add it to my answer. So now that's the head. I'm probably okay at this point. I have answer's head points to the same place as LL's head. We point to the same node, right? Well, then I get bucket 1. So when I add to the front bucket 1, I set head pointing to bucket 1 on answer, but then I set that guy's next node to point to the old head, breaking the list over here. Because I just changed this node's next node to no longer point to the third element of LL. Now it points to the second element of answer. So I can no longer actually successfully traverse LL. I've broken the link to the third element. Kind of make sense? So logically, this looks fine. And I gave credit for this. This is just fine. But the safer way of doing this, especially since I didn't say you had to preserve the list, but I didn't say you didn't have to, so a lot of answers here were okay, would have been to remove from a particular bucket and then add it to the front of the other one. So let's write we'll call this the pointer safe version of this guy. So I want to create my answer. Then I'll say while ll.getCount is greater than 0, answer.addFront ll.remove front. And then ultimately return the answer. So as I go through, I will be whittling down LL, physically removing nodes from LL, disconnecting them from the previous list. Remember how I've always kind of been kind of anal about making sure you fully disconnect nodes? This would be a reason why. Because I want to fully disconnect that node because I'm about to put it into another list. And I don't want there to be any extraneous pointers pointing to nodes that I didn't think it was pointing to, especially if I didn't update that node. Because then you might have something that you pointed out, where I could have the end of my list, but I still have this extra dude where it should be pointing to null, but I actually have it pointing, it's pointing to the middle of some other list somewhere, allowing you to kind of jump lists. But so it kind of makes sense what's going on there.
Should the return answer should be the same as the original list?
No, because I'm removing from the front of this guy and I'm always adding to the front of the other one. So I'm building the other one in reverse, but my second one is whittling down. So the front of my list is actually always just the next element. It just happens to be how my list is shrinking. So these both do the, on the surface, the same thing. This is more of a kind of a future warning that, and this is why drawing pictures with linked data structures is important, because this is one of those things that might be, you might write this and it looks very accurate. And then all of a sudden you get this very strange result and you don't know what the heck is going on. And that might be very difficult to debug, right? All of a sudden you get this, you'll get a null pointer exception your third time through. Because it can't get bucket I can't get bucket 2 of your original linked list because you've broken the link to it. Because the thing that used to live at bucket 1 now points to bucket 2, or now points to bucket 1 of answer, not to bucket 2 of your old list. So you've broken the original list, your source. And that might be very difficult to kind of figure out. You have to draw lots of pictures, and that would be one of those frustrating errors you spend 2 hours staring at until you finally realize that you were your own worst enemy. They do not get copied. Yeah. Well, yeah. I mean, when I say get it bucket I, I'm getting a variable here that already has something else pointing to it. So it's the same place in memory. So when I start breaking something in memory here, I've broken that link here to add the link here. You can write a method called clone. Instead of get I, you can call it clone I. And that guy gives you this brand new fresh node that just has the identical payload in it as the previous guy with none of the fallout. That would be a nice safe way of doing it. In fact, there's actually built into all objects in Java. If you go to the base object class, there's a function called clone, which will just give you that object as a new memory address. Now, keep in mind, though, that doesn't solve all your problems, because if the old object pointed to something else, the new one will point to that same something else. It doesn't clone everything in the line. It just clones the original. You could just build a brand new node. You could say node to return is equal to new node this.get payload. So you just build this brand new node that's hooked up to nothing that happens to have the same payload in it, and say, here, do what you want with this. This is like giving somebody the quarter, and they can run off and do whatever they want. It's not going to damage the original. But kind of a fun thing with linked lists. If I remember correctly, I think everybody pretty much solved it this way, or somewhere along those lines. So I think most of your solutions would have had the issue of the pointer problem. But I wasn't looking. I mean, that's more of those, I just saved you 2 hours at some point in your future type thing, as opposed to under test conditions. You're looking for the straightforward answer. I wasn't trying to trick you. It just happened to be one of those that had a kind of a side effect. So I did not take off points for that. What number am I on? 8. Write a method named remove@index that takes a stack and a zero-based index as a parameter, and it should remove the element at that index in the stack, leaving the rest of the stack intact. For this problem, position 0 in a stack is the top of the stack, so that's kind of if you wanted to use a get thing, but whatever. What do I call it? Remove at index. Am I not returning anything, right? I'm changing the original stack. Okay, remove at index. Oh, I need to take my index in. All right, so if I'm removing bucket 5, I need to, for example, I need to go ahead and keep everything up to bucket 5, right? Well, not including bucket 5. And then ignore bucket 5, and then keep everything after bucket 5. So a couple for loops with a result stack. So stack answer is equal to new stack. For int I is equal to 0, I is less than index I plus plus answer dot push s dot pop. All right, so we'll get all the stuff up to but not including index. Then we'll go ahead and abandon the bucket index. Just burn it off. It's gone. Then we'll go ahead and say for since we've been burning stuff off our list, we could even have a while loop at this point. So while not s dot is empty. We're just going to work with the rest of the stack. And we'll say answer dot push s dot pop. All right, so now when we're at the end here, answer currently points to our original stack with the one element removed. And our original stack currently has nothing in it. Right? So what I really want is I want my original stack to point to a place in memory that has its old self in reverse. So I can say s is equal to answer. So I've changed the value of s to now be equal to a new place in memory. What's wrong with this? On the surface, this looks accurate, correct? All the logic is correct. The issue comes down to this guy. Does this guy do what we think it does? This is another fun little example. I like to use exams as teaching opportunities without penalizing you on the exam. So tell me, what's the difference between pass by address and pass by value? If something is passed by value, we're getting a copy, right? And if we do something passed by address, what are we getting? Yeah, we're getting a pointer in memory. Now, when we hear pass by address, what does that mean to us? Typically means that if we make changes there, those are permanent changes. All right? This will not work. I'm trying to change the value of S. Now, S holds a pointer, right? It holds a place in memory. I'm trying to change that to be now the memory address that was stored inside of answer. The issue is that the value of S is a memory address. That guy is passed by value. The memory address itself is passed by value. When I get a memory address and I go to the place in memory and make those changes, here, let me show a picture. A picture is going to be good for this one. Love pictures.
You're getting a copy of the address as opposed to the address itself.
Yeah. So we have our S here. All right. And obviously all stacks look like this, right?
Stack, star, same thing.
Exactly. They both start with W. Ha! And by the way, this is one of those other really tricky things that when you run into a bug, that's why linked data structures, bugs are like the worst. If you don't draw pictures, like how many of you have been working on homework assignments and sat there for 2 hours staring at something, you just don't know why this doesn't work? All of you have had this experience at some point, right? I had this experience. I sometimes still have the experience. Sometimes I'm staring at a blank page and I don't know where I am. But that's a senility thing. That's something completely different. But years ago, I had the same problem. You've run into enough bugs and you figure out how to solve them and you realize that's just kind of the experience thing. But S points to this stack in memory. Now, any changes I make up here, we know those are going to be permanent changes. That's a place in memory. That's good. We're set with that. All right, so now we create this new thing called answer. Well, that's not going to fit in there, is it? Oh. Nailed it. All right, so we create this new thing called answer. And as we're going through our code, this guy's getting emptied out. This guy's getting filled up. Right? Now, in the end, I'm going to go ahead and I'm going to show two different versions of S. Now, we're not sure what S was called out in the original program, but we do know for, oh, wait a minute, where's my colors? Don't I get color? Oh, I have more than one thing select. There. We do know that the original would definitely be colored green. It's just a known fact, given information. All right, so whatever that guy was in the original program, whoever called your remove at index, they had some stack that pointed to the same place in memory, and that's the original. Then we pass that guy in as this variable right here, okay? So both of these guys point to the same place in memory, okay? But the value of both of these variables is a primitive type. It's a memory address. Make sense? That is passed by value. It's telling me where I can go and mess up memory, but the actual value of S in both of these is a static value. I can't change that. So I'm just gonna, just for the sake of argument here, we're gonna say it's 100. And of course, that would be red. This would be so much fun with finger paint. It's got to be kind of disheartening. You're in college, your professor's up here talking about finger painting. What is it? Life is like a circle, right? You start off, you're young, you play with toys, and you get older, things become serious, and then just right back down. All right, so comes in now. Both of these guys are pointing to the same place in memory, right? And we'll go ahead and we'll assume that answer here is memory address 200. Just to keep our numbers simple. Okay, so all of our logic up here, all this stuff is all good stuff. This stack is shrinking, this stack is growing. We're all good with that? That's happening. No tricks there. It's this very last line that becomes a problem. This S is this guy right here. So locally, I'm changing S to point to this new stack that I've built, which means that S's value changes to 200. But when this function ends, the scope of S, this local S, you know, maybe this guy was called my stack someplace else, something like that, even though it was passed in as S. But you know, it's another variable that just happened to point to the same place originally. So I update when I say S is equal to answer. I'm saying the value of S, which is a memory address, is equal to the same value of answer, which is a memory address. So I'm changing S to be 200. So now S and answer both point to the same place. Everything looks legit. But now when this function ends, the scope of all the local variables in this function disappear. So all of these guys are now gone. And when you go back to your original program, the variable that was passed in for S is still pointing to memory address 100. It is now pointing at an empty stack. We emptied it. We didn't remove. We removed a lot more than just index. Does that make sense? So what? Oh, go ahead.
So you're saying that my stack is like if you were in your main function and you called that function.
I'll write it real quick.
You'd be bringing, or you'd be taking it into my stack, or you're bringing in my stack.
My stack is equal to a new stack. Something like this. Let me left justify this. And then I'm just going to do fill my stack with stuff. So we have some code that fills it with some stuff. Then we're going to go ahead and we're going to call remove at index my stack and let's say 4. So that's my main program somewhere where I have a variable called my stack. It's filled up with some stuff. I pass it in to remove at index. I pass in my stack. My stack comes in for this variable called S. So both those guys are pointing to the same place. So that's like the scenario. That make sense? Yeah, so this becomes, so the lesson here is this whole idea of pass by value versus pass by reference. So what we can really say is every single variable that every parameter that we pass to a function is always passed by value in terms of its core value. Memory addresses connect to a place in memory that if we were to change that place in memory, that's a permanent change. That's what we mean by pass by reference. But we can't modify the value that's actually stored inside of that variable. Make sense? We can modify the stuff that's stored at the destination that that variable points to, but I can't modify the value that's stored at in that variable itself. So what's the fix here? Well, in terms of this, so I have this guy. How do I duct tape this up to ultimately make sure that S holds its old self with go ahead.
Push everything from answer back into S.
All right. So I'm going to pop from answer and push it onto S. What's going to be the problem with that?
We'll get it backwards.
So we'll have it backwards. How do I fix that?
There's a way to pass by a reference in Java.
Oh, you mean like in out like in C#?
Don't you
Not
use
unless you
an
get
asterisk
the
before that will bring you the pointer instead of the.
Yeah, not in Java. Yeah, you don't have that syntax in Java. So I need to really fix this. So you just gave me a solution. So what he wanted to do, let me scoop my pictures over. I don't want to mess up my artwork. All right. So the solution he suggested is so this guy's a no-go, right? So what he suggested is I can go ahead and I can now copy everything back into S. So I can say while not answer dot is empty, or I can say, while peak, answer dot peak is not equal to null, something like that. However you want to check for it being empty. We'll go ahead and say s dot push answer dot pop. All right, and then ultimately when this is done, S will have stuff back in it, but it's going to be backwards, right? Because that what I effectively just did there is I reversed the contents of my correct solution. How do I fix that? Huh?
Pop it out. Pop them out and move them back.
Like give them a temporary.
Yeah, give myself another temp stack.
How is it? That's how.
Stack temp is equal to new stack. And instead of pushing this into S, we'll push all this into temp. Then we'll say while not temp dot is empty, S dot push temp dot pop. Now we got it. So this first thing is we're taking answer and we are storing it inside of temp in reverse. Because then we're going to need to take temp and empty it into S in reverse, which is now in the correct order. That make sense? So not hard code, but kind of annoying stuff. And this all comes down to how pointers work. All right, so questions about that? It's another fun little, go ahead.
Even in the old solution, wouldn't we also have a problem? Because even if we could somehow set my stack, the original pointer to point to answer, wouldn't answer just get deleted when we exit the scope, and so we're ending up pointing to?
No, because my pointer count would be 2. I'd have 2 separate variables both pointing to that place. So when S is pointing to it and answer is pointing to it, my pointer count would be 2. When the function ended, my pointer count would drop off to a 1. What you're saying is the reason why it doesn't work. Anyways, because your pointer count would drop to 0 when S and answer disappeared, because S is a local variable of this guy. But let's assume that you didn't understand that problem was there.
Right.
You would have 2 pointers that both pointed to that place in memory. Only answer would drop off. So you still have one thing pointing there. So you wouldn't have your pristine stack garbage collected, is what you were getting at, right?
But that might happen in other languages, or not likely?
No, I think every language, when you pass something in, I want to make sure there isn't an exception that I'm aware of. Because obviously I'm aware of everything having to do with programming through the history of programming.
Right, so we have to account for COBOL and Fortran.
I know about those. I know about those. I think it's a pretty safe bet that you can say that parameters are always passed. The value that is passed along with a parameter is passed by value. If it happens to be a memory address, it's called passed by reference because that points to an actual place in memory that if you start changing stuff there, those are permanent changes. But what you can't do is you can't change the original. In our case, it would be the base address of that array. That thing's not changeable. that's going to revert back. Make sense? That's kind of a fun one. Yeah, so again, if you didn't write all of this, including the annoying reverse and then unreverse thing, it's a 0.
If you could do that, would you do this?
Probably. But the bottom line is anybody who would have done something like this has shown me they truly understand how it all works under the hood, right? But so it would have been worth extra points, but it would have been meaningless to me because that person's probably already getting an A in the class. They're just going through the motions. All right, what number was that? That was 8. Oh, I'm out of programming stuff.
I got really overwhelmed with the programming one.
But those were the easy ones. They were so much fun.
I mean,
Wasn't this
they
fun?
They were fine to do them, but like in the moment, it's like, oh my goodness, I have to keep each problem straight and only focus on one.
So it was stressful. Oh, good. I like that. Yeah, my 450 class this semester, I had to curve the heck out of the exam in there. And it was like so different for different students in the class. So there was 10 questions. I ended up just counting their best 7. But there were several people in the class that finished all 10. But just kind of like, it took the full time. But then other people only finished like 6 or 7. So I figured, whatever. So I had these like crazy grades. I had like way too many people with like high 90s. And then garbage. Well. All right, number 9. What does the following method do? Okay, this guy returns a stack called do something, takes a stack, create a new stack. While the stack's not empty, we do a couple of peeks and pushes. Okay, so this creates, so similar to what we just saw, this will create the original stack S in reverse inside of temp stack, but each element will be duplicated twice. Make sense? All right, so that's what that guy does. Reverses S in temp stack, but each element exists twice in temp stack. And then we return that. Questions about that one? All right, number 10, what does the following method do? Linked list do something. So, okay, so takes a linked list and a pause. Oh, yeah, this one's a good one. So this guy takes in, so we have a brand new linked list called answer. We set cur node equal to, we get node from pause. And notice I have a little comment there that says this returns a node without removing or disconnecting it. All right, and then we're going to add that to the front of cur node. All right, which, well, this should be fine. So adds to the front of cur node, then we return, adds it to the front of answer, adds cur node to the front of answer, then we return answer. So if we show a picture of this one's a good picture. So ultimately, what does this guy do? It gives you a second pointer to the original list. Watch the picture. So we have, what do we call it? We call it linked list. So we have LL and we have answer. Okay. LL. The capitalization stuff is really annoying. We have answer. All right, I'm just going to give myself a little 3-bucket linked list up here. right, there's that guy, and then Li points there. The answer starts off by pointing here. All right, so the very first thing we're doing is we're getting bucket 0 of this guy, right? And what does bucket 0 of this guy do? We get a copy of that. But it doesn't change or disconnect this one. Doesn't remove it. So that means that this guy still has a next pointer that points to the rest of this list. So I have two different linked lists that have a head that's the same node. And the rest of both of those lists are the same list. As opposed to thinking that this guy is a list containing one node. It's actually a list containing one node that already is linked to a bunch of other nodes. Make sense?
Because you didn't disconnect it.
Yeah, because this guy never actually got disconnected. When I brought it down here, it's not like this guy was forcefully removed from this and then this guy was updated. If that was the case, then I'd have this guy down here with this pointer to it, and I'd have a one list. But instead, because it wasn't forcefully removed, I just got a copy of this node. This node has a next node that points to this guy, just like this guy has a next node that points to this guy. So I have two different lists that point to that have two different places in memory, whose head points to the same place in memory. Right? So effectively, it's going to actually look like this. But this guy might have memory address 100. We'll make that red. And this guy might have memory address 200. So these are the memory addresses of the linked lists themselves. And then they each have a variable of type node called head. It's head that points to the same first node. So this guy's head points to this memory address. This guy's head points to this memory address, even though these are two separate linked lists that live in memory in different places. Make sense?
Can we draw pictures in our next exam?
You can always draw pictures on exams. You might even get extra credit for drawing pictures. Oh, I think that's a pretty reasonable assumption. I would give extra credit for pictures. Doesn't that seem like something I would definitely do, as much as I like drawing pictures? Oh, it's so fun. I'm not very good at art, though. You should see me at these paint nights. Well, you see some of my pictures in my office.
I almost failed now. I really hate art.
Yeah. Well, my wife drags me to these paint night things where you go there and you drink a bunch of wine, and then there's like an art teacher that teaches you,
Yeah, I know.
there's like a fancy painting that you're supposed to do, but I always go off script. I don't paint whatever they want me to paint. No. Yeah, I got in trouble last time I was painting with my food. We've already established that. This isn't new news to anybody. Well, I needed the painting that we were painting didn't have any brown in it, so I didn't have any brown. Well, I had some barbecue sauce from my my appetizer thing. Barbecue sauce is brown. Right? So I use that. Does not work well. It doesn't dry like paint dries. It's different. Just so you know. You probably already knew that.
Change colors?
No, it was the right color. It's just not the right. It never actually dried. So the art lady brought me some brown paint. So we had to clean up my painting a little bit. So I could use my brown paint.
What did she think?
I don't know. Everybody, I think they just treat me as special needs. there's not a whole lot they can say. One of my best art pieces that was in my office, I drew the Android logo. That one actually looks like sort of kind of legit. And I did a Pac-Man with Ninja Turtles. Yeah, I draw whatever there's something funny. And everybody else is like spending all day, they're all stressed out. You know, like, oh, I need to make my trees look perfect. Like, it's so hard to draw branches. Why are you getting stressed out over drawing branches when you could just draw Pac-Man? See, I have fun at those things. All those other folks are like all stressed out. So I think I'm. That's it. Perfectionist. I'm just there to pass time. And apparently pay for these paintings. They charge you for this. It's like $50.
Drinks for free.
No. No. Yeah, so my bill ends up being significantly more than $50. Because there's a lot of time you have. Because sometimes you're sitting around waiting for paint to dry. Isn't that like an old joke? You're sitting around waiting for paint to dry. And the really dumb ones, when you have to have like when your canvas is supposed, you have to paint your canvas white. It's already a white canvas. It's white or off beige or whatever. So you spend the first 10 minutes with white paint painting white. And then you got to sit there for 20 minutes while it dries. Why didn't you just give me a white one to begin with?
It's a base.
Well, that is what it is the base. But they couldn't just dip this like a stamp, like just dip it in white paint and let it sit there and dry before we got there? Just garbage. All right, yeah, so that one creates a link to the next dealy flippy thingamajig. All right, questions on that one? All right, questions on the exam as a whole.
Can you explain your thing, the memory address? So,
This guy?
so they end up pointing to the same.
Yeah, I'm gonna expand these a little bit. So we're gonna say that this guy has memory address 700 for that node. Each of these guys So this linked list has a memory address of 100. It lives in memory somewhere, the linked list itself. This linked list has a memory address of 200. It lives in memory somewhere. But now each of these have their own local variable called head. That's going to be a node pointer, point to somewhere in memory. So in the end, the value stored in head for both of these is going to be 700, which points to the same node in memory. So it's that guy that points to the same node in memory, even though we have two separate linked lists. So in this case, answer and LL. Yeah, so that's the example I have here. These guys, those variables point to a different place in memory themselves. But a linked list is just a kind of a container for holding the logic of the linked list, right? So really the beginning of the linked list is LL's head variable, or answers head variable. So even though LL and answer are two separate linked lists that live in separate memory locations themselves, they both have a head variable that points to the exact same place in memory. That was a fun exam. Especially the programming ones. There were two really good lessons in there. It was good. All right. Any other questions? Comments, concerns, bribes? Remember, if you did crummy, policy is if you do better on the final exam than you did in the midterm, I'll replace your midterm exam grade with whatever you got in the final. So, this isn't a death sentence or anything. But actually, as a class, I think we did all right. I had one class yesterday. I gave back an exam. The lowest grade was a 7. 7%. How do you get a 7? Yeah. Well, yeah, but I mean, the exam was written with that being considered, that they don't know anything. So it was like written to be an easy exam. I mean, the high grade, there were several 100s on it. It wasn't like it was an impossible exam. How do you get a 7? All right. I will see everybody on Thursday. Remember, for a couple things. It's a good question. Really, that's actually a good suggestion. There's 2 ways of looking at this. How about I do this? How about on one hand, there really should be Bible homework given that it's Easter week. On another hand, since it's a short week and some of you are going to be traveling and stuff like that, there really shouldn't be Bible homework. I would strongly encourage you to read one of the Gospels this week. let's go that route. Okay, but I won't actually have Bible homework. Remember today, student, faculty, staff Bible study, God and Grub. Go to the cafeteria, sign in, you get free lunch, take your tray down to the terrace room or whatever it's called, and grab some lunch. Also remember, Thursday we do meet, but any classes that meet after 4 p.m. on Thursday do not meet. So you have Friday, Saturday, Sunday, and also classes that start before 4 p.m. on Monday do not meet. All right, so Monday you have off unless you have an evening class.